Okay, let's see. Today's topic is about responses. Right. So we are talking about on system responses. This is quite short introduction actually, but there are quite a few topics there. Important topics, not too many, but actually very important. So yesterday, well, let's start from Monday. Monday we actually learned how to make these different kind of signals, how to make sinusoid frequency signal, how to generate some noise on the top of it, how to make these unit impulse, unit step functions, and how to plot them and save the data for further viewing. Then on yesterday we actually visited the systems, how these systems are described in this kind of mathematical environment. And well, it's all about the system characteristic properties which are defining both the difference equation, also the transfer function. So the system coefficients or system parameters, A's and B's. So we have this difference equation where we have the weighted outputs. Sum of weighted outputs is just equal to sum of weighted inputs, where we have the B, A's on the left-hand side on the as multipliers of the output and the history, and then we on the right-hand side of the equation we have the B's, which are actually the weighting parameters for input and the history. Okay, and exactly same parameters A and B are also present on the transfer function. On transfer function, they are actually polynomial coefficients. Okay, good morning. Today, so basically today we are going to look at closer look at the system responses, how we can actually analyze a system. So basically, most important response of all is the impulse response. And now I would like to actually use some other view since I want to go to the whiteboard again. So basically, the impulse response is simply when we have the system F, or well, we can call it also like that, mark it with the transfer function, and well, this is just mathematical marking. And if we have an impulse in, then basically what comes out is the impulse response. So this is the definition. The real definition, what is the impulse response? So impulse response exists to any system. If you have a, for example, audio equipment that you want to measure its impulse response, then you would just run the impulse through it to get the response. However, on analog systems, it's impossible to do. Let's see, do I have? Yeah, I actually have the same picture here. So, for example, when you have a example, a 4-point average filter, it's simply replacing the X with the delta. The systems with no feedback are very easy to define what is basically the impulse response. It's the same as the vector of coefficients, system coefficients. So without feedback, you always get that kind of result. Maybe I should actually mark it with another color here. So B0, B1, B2, and so on. Okay, that's the impulse response. But in this kind of systems with no feedback, we actually sometimes just mark this H0, H1, H2, and so on. Okay, good. Of course, this is, as I said, impossible to measure from for a the audio, the analog systems. So what can we do for measuring the analog systems on digital domain? Well, remember, delta function is also mu of n minus mu of n minus 1. So basically, if you run the mu and measure the, let's mark it h of s, an analog system. So you run, for example, audio system, you just take the this step function from your sound blaster, or function generator would be better, and just measure what comes out here. What comes out here, that's actually the step response, what you are recording. And you get the, if the system is linear, then this is actually the same as, oh, sorry, that way. So you can calculate the impulse response from step response. So this is just a time delayed step function, or step response. So basically you can easily reconstruct the and measure the impulse response for any system, analog or digital. Okay. So yeah, well, that continues the impulse response. Okay. I actually put this one as you know, non-ending for this reason. So actually there's a division between the different systems based on the impulse response. There are finite impulse response systems where basically you have a finite number of the values on this one, meaning it ends somewhere, or infinite impulse response. Basically, the error is, the difference is, let's mark it like, I have different colors, so IIR, and then on the same picture I will have FIR, if that is the impulse response picture, H of n. So for IIR, you have something which goes and goes and goes and never ends. So even after waiting for days, it still has some remains of the signal there. While the FIR system would, I'll just draw it a little bit different here. For example, like that. And then it goes to 0 and continues to be 0. Those are 0 at this both. So finite impulse response system is simply a such kind of thing that this impulse response ends. It has an endpoint. Most of the natural systems are infinite impulse response systems. Actually, finite impulse response systems in nature are mostly just like the in atomic level, where you have quantum effects there. Okay. Otherwise, for example, RC filter, simple RC filter, you know that it never reaches the final value. It just approaches it but never reaches. And same thing for any analog filter. Some of them actually approach faster to the final value, but generally speaking, natural systems are infinite impulse response systems. Although for digital systems, finite impulse response systems have some really good properties. Just a note here about the feedback. Having feedback doesn't say anything about being infinite impulse or finite impulse response system. Remember the 4-point running average system. You can actually do the same system with feedback, but it's still finite impulse response system. It still does this 4-point impulse response if you measure it. Okay. Okay, then how does the transfer function and impulse response then actually relate to each other? Well, so basically the let's see how to explain this one. Okay, so basically the system transfer function for LTI system, it has to be linear time invariant system. Most digital systems are, but anyways, the you basically just take the Z transform of the impulse response. So the transfer function, okay, is the Z transform of impulse response. Okay, practically meaning, if a system has a finite impulse response, then these parameters would be also the system coefficients. Okay, which also shows up in the this 4-point running average filter. More stuff. How you can say from zero pole plot if a system is FIR or IIR. That's probably the easiest way of checking if the system has finite or infinite impulse response. You check where the poles are. Poles can be, for FIR systems, poles are always either at the origin or at the same place as you have the canceling zero. So, for example, these are both the 4-point running average system, zeros and poles. This one here is the normal. This is with the feedback. So feedback, remember, it actually makes the system 4th degree. It has 4 poles, so there's the yn minus x n minus 3 there, or for, yeah, x n minus 4 there. So basically that makes that pole there, but also on the downstairs you have the z minus 1, which has a pole here. So they're canceling out. Okay, as it did on the transfer function. So basically these cancel out. They don't affect on the final result, but so basically it's the finite impulse response system, because of all the poles are at 0 or canceled out. The IIR systems have always at least one pole of the origin, preferably inside of the unit circle, then it's also stable. Okay, that's basically, you can take a quick look on the zeros and poles, and it immediately shows you if a system is finite impulse response or infinite impulse response system. Okay, good. So should I actually draw it also here? Nah. No, it actually fits. So complex circle. It doesn't matter where the zeros are. They can be anywhere. Basically, they can be even like that. It doesn't affect on the stability or nothing. It just affects on the system response, the frequency response, especially. Then for the FIR systems, you have multiple poles on the origin. But if this is a IIR system, then you have pole pair like that. Well, what should I actually IR? So you have pole pair outside of the origin, something between 0 and the 1. All right. Oh, that flash really helped a lot. There we go. So, okay. So impulse response, easy to find out. You just run the signal through a system, you get the impulse response. Then it can be either finite, so it ends, or infinite, it doesn't end. For linear systems, you can actually measure the impulse response also by using the step function, which then you just need a simple filtering to find out what is the impulse response. Okay. Transfer function is always the Z transform of impulse response. Okay. Wow. So step response. I already have the step response. So basically, same thing as for impulse response. Step response is the system output for unit step. And yes, you can measure it. Okay. Arbitrary signal response, meaning what the system does for any signal. Okay, it can be calculated from the difference equation. Just a reminder, this is not usually the most efficient method or most accurate method either. So this you already saw. So basically, arbitrary signal response. Sometimes you need to optimize the system such that it actually does the least amount of calculations. Okay. Um, right. So those were the some of those responses. I think I added something here. Probably need to take another picture. There. So next, how about the frequency response? So the impulse response and unit step response are time-based responses, but the frequency response is the frequency space response. Okay, it says it there. So frequency response is actually same as you take the transfer function and evaluate it at unit circle. Okay, and then I have a couple of the formulas there. Unfortunately, those look ugly. I haven't fixed those yet. But anyways, let's draw it a little bit nicer looking. So we have basically the k from 0 to n bk times z to minus k. Z is now e to jk, e to minus j omega, divided by k from 0 to n ak e to minus j omega. Sorry, k is missing. Okay, there. K. Ha. So what comes out is you have, well, the product form of the same thing. B0 over A0 is the gain of the total gain of the system, as we decided last time. And then we have a product of let's see. So this is the product form, meaning we have found out the zeros and poles, and we have basically a product of the z minus the 0. In here we have e to j omega k. I think that's the one. No, that's the e to j. Okay. So this actually would be the z minus zk on a product form when you calculate the roots of that polynomial. Okay, minus zk. And the other one is product of k equals 1 to n e to j omega minus pk. All right. What I'm actually up to on this one. So we can also, since this is a complex number, evidently this is a complex number, so you have e to j omega here. If you use the Euler's formula, you can then divide it into real and complex, or you can also divide it into two parts, which one is the magnitude, simply the magnitude of that one, so absolute value. So that's the amplitude response or magnitude response. And the other one is the phase response. So you have E to J theta omega. And that part here is the phase response. Okay, magnitude and phase. Let's take a closer look at those. I first need to take a picture. I'll let that one be there still. Or actually, let's continue from that corner. Okay. We have the zero pole plot. Let's keep it simple. I've just put a couple of zeros here and a couple of poles here. Wait a minute. Let's make it easy so that we can actually test it with the MATLAB. So we have pole location is 0.5 and 0.5 J, and then of course we need to have the complex conjugate pair for that one, and then we have this another that I will actually define by the complex angle. So that's at range of 1 at angle of let's see, that's pi over 2, that will 3 pi over 4. Okay, good. So those are the locations. Let's think of that a moment, and then we have this, the value of frequency response at point EJ omega. It is a point at the unit circle at angle omega. Simple. And first, if we basically think what is the amplitude response, let's mark the amplitude response somehow. So that's the complex angle omega. By the way, the mapping of this omega is quite simple. Well, there we have the omega actually is the how does it go? Physical frequency over the sampling rate times 2 pi. So 2 pi omega equals the sampling rate on this the complex circle. Mapping. So we know where the physical frequencies are. Okay, so basically let's first sketch a little bit what happens to the magnitude response at different angles. So we have B0 over A0, and then we have a product of e to j omega minus zk second norm. That is distance. Distance of point e to j omega to zk. Same thing here. this one is a distance. Maybe I should mark it here. So it's green. No, So just coloring up. So basically, we are talking about the distance of this point to here. And then we multiply with the distance of this point to here. This is e to j omega minus z1. If this is z1, this is z2. Same way, that's a distance of e to j omega to z2. Likewise, this actually, on the numerator, we have the distance of ej omega, oops, not that omega, capital omega, minus p1. And we also have the distance to p2. So those are actually just the ratio of the distances to ratio of product of distances to zeros divided by distances to poles. Okay, so it has kind of nice geometric explanation. Let me mark a couple of angles here. So we have the pi over 2, 3 pi over 4, pi over 4. So what happens when the j omega is exactly here? The distance is 0. So we have at this 3 pi over 4 angle, we have amplitude response is 0. Great. And also in vicinity, the amplitude response actually remains very small. So we can actually mark it like that already. On the opposite side, at the pi over 4 angle, since this is okay 0.5 and 0.5, so angle is pi over 4, we are in a close distance to this pole, which means this goes to minimum. When this goes to minimum, basically the whole thing goes to maximum. So we have a local maximum right here. Depending how close this one is to unit circle, you basically have either peak here or a kind of flat valley here. So I'm just guessing this might actually look something like this in here. Maybe. We'll see it later. And there's nothing else that actually affects on the this amplitude response except those two special points. Oops, maybe I should draw that one in different color, meaning that we can actually just connect the dots, something like that. So that's our amplitude response, which is calculated or estimated directly from the unit circle and Argand's diagram. Okay. And there is the, frequency response of 4-point running average filter, which actually comes as a nice, when you have this kind of running average filter, then the, these actually, you can even calculate. It's just cosines and sines and ugly imaginary units or such, but fortunately we do not need to calculate it like this. in reality, we have on Octave, we have function to do it for us. Okay, so that's about the frequency response. Yeah, okay. Let's see what else I have. So yes, we have this frequency scaling. So we have this angular frequency, or basically it's normalized angular frequency, what we are calling it, which is simply directly proportional to physical frequency. The highest frequency on this unit circle is the sampling rate, which is basically here. So sampling rate over 2 is here. And this basically is the aliased spectrum here. So basically it's aliased to the corresponding positive side here. But, well, that's just philosophy. So anyways, that point here actually, that's where the circle repeats itself. It's 2 pi, and that's the same as how often this discrete times sample frequency space is repeating itself. Okay, so yeah, omega is same as physical frequency divided by sampling rate times 2 pi. Good. And there's an example. On previous example, I had just from 0 to pi here, not 2 pi, only that part. That's interesting part. Since this is just a mirror image, and the sampling rate of 44.1 kilohertz. Actually, the sampling rate over 2 Nyquist frequency is 22.05 kilohertz, and that gives a notch, meaning very high damping ratio at 11.025, and at the highest rate. But, well, okay. Now speaking about filter, running average filter. If you think of this as a low-pass filter, this is not a really good low-pass filter. This is then the stop band, and you have stop band attenuation only minus 10 dB. That's not good. But it reduces a little bit of noise, but not too much. We can do better. Ooh. Oh, okay, if you want to see the animation, you just click the click that slide. Let's see, does it work? It's animated GIF. Oh, okay, yeah. So it actually works. Wow. So that's where the that's the EJ omega right there, and this is that 4-point running average filter amplitude response and the 0 pole plot. Wow. Do I close that one? There. All right. So, yeah, same picture in here. Wow. So more animations actually are moving zeros and poles, and then animation about the flat response. Hey, well, this was so much fun, so let's take a closer look on also those those plots, but I need to then change this one. Okay, let's see what kind of animation do we have here. Okay, that's what happens when you just move the zeros on the origin. So I have a zero pair located at the unit circle. And now I'm actually moving the pole. I think this is a double pole actually what I'm moving. So you can actually see how when you get closer to the unit circle, you get higher Q ratio of the filter. And moving along the close to unit circle, it actually just put some more the gain on that particular angle. Okay, this is actually it was nicer picture than I thought. And you also can see the magnitude, meaning the gain is also changing. So when you're moving the pole closer to unit circle, and if you like to have this still a unity gain amplifying system, then you would need to scale it. Okay, that was nice. What was the other one? Flat response. Oh, okay, flat response. So that's one way, say way of doing a flat response filter. So basically, you have these zeros here to have the maximum attenuation on those angular frequencies, and then you actually adjust the gain here. So you actually push a little bit gain here, but more closer to the gain closer to this edge of the filter, so you actually have a flat passband gain. Nice for audio filters. Okay, what is the next? Good. So let's go back to the business. Phase response. Phase response is a little bit, say, harder to analyze. Well, not the Winter computer is not, but I haven't found a graphical tool to do it yet. So the phase response is something that you always need to calculate. Okay, that can go. And now we actually talk a little bit of, so when we have the H of E J omega amplitude response path and the phase response path. This one here, think of a system which has the, sorry about that one, that's an artifact from the picture making routine. So if you have a system with that, wait a minute, maybe I should just mark it with the H of EJ omega. And you basically run a sinusoid. Let's mark it with, so it's easier actually to think of it as a physical system. So I just mark it a continuous time. If we have a continuous time system, and we actually run a sinusoid signal there with amplitude, okay, amplitude. Wait a minute. let's make the amplitude 1. It's easier that way. Amplitude 1. What comes out is the amplitude response, meaning the gain at that angle, at that frequency, and then you have the sinusoid with phase shift. All right, same thing in digital and same thing in analog systems. So this actually is the phase shift of the signal. So if you are looking at this one on oscilloscope, all right, and you have the well, maybe it doesn't extend over the edges. So your test signal is here. Then basically what comes out is something else. You have the maybe something like that. Meaning that the amplitude has changed. If this one was 1 here, then this would be the A at omega. And then basically, well, I will expand that one. I'll connect my computer and then analyze it further. So that one, if that is 1, then you have the shift, okay, phase shift and also the magnitude change. Then that is A at this frequency, and this one here is the phase shift. In angle. Okay. There. So that's what the phase response actually is. It's time shift in particular. There are different phase responses. There actually is also zero phase response. It's in digital world, it's possible also to reverse the time, not in real time, but you know, on post-processing of the data, you can actually have zero phase response systems, meaning that you don't have any. This one is 0 at all time. The simplest way is basically take a data, filter it one way, reverse the time, do it another time. It actually does doubles the effect of the amplitude response, but it also reverses the phase shift. Whatever the phase shift was, it's not anymore. It's 0. Okay, but any other system, and these would be the real-time systems. That's only for post-processing. So we basically, the linear phase response is something that we usually prefer. Let me mark it on the same. So talking about linear, the phase response. So phase response as a function of the omega. So linear phase response. So remember a couple of slides away there. Can we actually return to those? Yeah. That's frequency response for 4-point running average. That looks linear. And yes, it is linear. Good thing. So for linear phase response on the pass band, only that matters is actually what happens on pass band. And it can be either linear, or then it also can be anything else, so non-linear. The real difference actually comes when we actually calculate the group delay. So the group delay, I think I will leave that one there. Is a measure of how much the actually signal wait a minute, this has some funny markings again. Okay, so group delay is actually d of omega, not d of theta. There's an error here. So it's a derivative of the phase response. And that's actually directly the time difference on the of the signal. Time delay. So if we have that sine omega t plus theta of omega, actually that's the same as sine of omega t plus d omega. There. So I've just, changed the angle delay to time delay, and by taking the first derivative. Okay. So what happens if we have a group the linear phase response? Linear phase response actually means that there is so phase response is in form theta omega is as in here. There's just a scaling factor k, or the what is that? Let's see, angle k times omega. And then when we calculate the group delay, you can find quite easily that this k times omega derivative over omega is simply k, which is a constant. Good thing. Think of a system, a telecommunication system. For example, dual tone multiple frequency. So they have different frequencies added together to make their dual tone multiple frequency, and then you have any system here. How do you want that system actually to handle these different frequency data? You want them to come out the same time. You don't want a time shift in between of these frequencies. So basically, for telecom, you must have a linear phase response. So then these time differences between different channels of data are still at the same time. All frequencies appear at same time. Very good for reconstructing the information. Good. And then if you have a nonlinear phase response, then basically what happens, well, of course, this is not constant, but it varies, meaning that we have a variable, like in here, we would have a variable varying time delay of different frequency signals. It means that it starts queuing the pulse shape. That might be okay, but well, for telecom purposes, or if you are measuring some pulses, pulse shape, then that would really do bad things for the pulse. That's variable by omega. Good. Although with a nonlinear phase response, if you can basically tolerate that one, then basically you can get a say more effective filters. With the linear phase response filters, you are actually tied into finite impulse response systems. So, but with the infinite impulse response systems, you can actually have, say, high Q filters easily. You just put the pole close to unit circle, which are actually really good for audio processing, for example. So this thing about the linearity or non-linearity is not about good or bad, but more about the what suits the best for the application. Okay. All right, and there I have an example. Let me put that one like that. Shows better on my recording. So if we have, for example, this kind of square shape signal, basically the that kind of test vector and run it through the system. If you have a linear phase response, then basically means that what comes out, if you have a symmetric input on both edges, it comes out as a symmetric also as in output. That becomes from the, well, from this one. So all the frequencies are appearing at the same time. So basically it follows a nice, so there are no surprises on either edge. Okay. If you have a nonlinear phase response, you would start seeing something like that, which is, well, you have seen probably this kind of behavior on the, say, analog filters on second order or higher. When you hit a system with a step, it goes up and then it has some ringing. Same way, when you go down, it goes down and then some ringing. So this is asymmetric behavior. Okay, then I also mentioned the zero phase response. I actually took exactly that filter, nonlinear phase response filter, and run first that test signal to system like this, and then I took this signal and reversed the order and put it through the same system. This one comes out nice and symmetric on, well, basically symmetry axis is here. Both sides, same behavior. Easy trick. cheap trick. All right. So that's basically all for the system response part. Of course, when we are doing a system design, we also need to consider what is our signal, what are the properties of our signal. And that, I think, is already something you have done before. So spectrum analysis of signals. So we have the spectrum, power spectrum, which basically describes the distribution of signal power into frequency components, and that's done simply by doing the Fourier transformation. And there, this power spectrum is basically Fourier transformation of signal multiplied by the complex conjugate of it. And yeah, actually, we had this slide on Monday already. We didn't have the practice though. And this was also on Monday. And I think this one was also on Monday slides. So just a reminder of that when we are actually dealing with the systems, never forget that it's done to somehow change the response. Somehow change the behavior of the signal, or filter something out. Okay, that was fun. My favorite topic. So again, I have a kind of questions for self-study. Please go ahead if you feel like it. Go and test how well did you actually. It might actually be also well. I have no idea. I haven't checked that one actually before coming here, but I think they're good questions. So we will have a short break or long break. It's just about the lunch time. So lunch break. And after the lunch break, around 1 o'clock, we can go on for the laboratory tutorial. Good? Okay, thank you.